All right, you made it. Finally got to the last video. So remember that in the previous video we talked about carbohydrate metabolism. And so if we're going to break down a molecule of glucose, there's really three parts to that process once that glucose is inside of, say, a muscle cell, for example. So we're going to take the glucose and we're going to break it down initially anaerobically using glycolysis. And so once we take the glucose molecule through the 10 steps of glycolysis, the end products are 2 net ATP, 2 reduced coenzymes, so 2 NADHs, and then 2 molecules of pyruvate. So then the pyruvate we're going to take from the sarcoplasm, so from the cytosol of the muscle cell, and we're going to move it inside, or actively transport it inside of the mitochondria. And so once pyruvate's inside of the mitochondria, then it's going to go through the citric acid cycle. And through the course of the citric acid cycle, we're going to produce 2 more ATP. We're going to produce additional reduced coenzymes, so NADHs, FADH2s, and then we're also going to produce carbon dioxide. And so then what we're going to do is take the hydrogens that we've pulled off of what started out as pyruvate, and we're going to shuttle those hydrogens over to the electron transport chain, where we'll pull the electrons off of them and we'll use the energy from those electrons to pump hydrogen into the intermembrane space of the mitochondria. Because remember that mitochondria have 2 membranes, the outer membrane and the inner membrane, so we're going to pump hydrogens into that intermembrane space. And so then we're going to create a gradient where we got a lot of hydrogen in that intermembrane space, and then we'll allow hydrogen to flow with its concentration gradient back inside that inner membrane. And when it does that, we're going to direct it through, or it ends up going through, a protein called ATP synthase. And so that protein then, as hydrogen moves back inside of the inner membrane, is going to spin, and that's then going to rephosphorylate adenosine diphosphate and make a new ATP molecule. And remember, then we're going to get rid of the hydrogen by attaching it to oxygen and making metabolic water, and then we can get rid of that. So that's why oxygen is going to be important in the process. So with respect to carbohydrate breakdown, one of the things I talked about yesterday was, there's this stepwise fashion of breaking down the macronutrients, so carbohydrates, fat, and protein. And really what we're doing is we are pulling off hydrogens, and then we end up with carbon dioxide, and then the hydrogens, again, we're going to get rid of by attaching them to oxygen to make metabolic water. And so yesterday when we talked about glucose, remember that the chemical formula for glucose is C6H12O6. Well, what you can see here with lipids is that lipids have a much higher ratio of hydrogen to oxygen. So you can see here stearin, which is a pretty typical fatty acid. Its chemical formula is C57H110 and O6. And so if the idea is that with metabolism, what we're doing is pulling off hydrogens, well, if we've got a lot more hydrogens that we can pull off of a molecule like stearin to send through the electron transport chain, then we're going to get a lot more ATP from it. So remember that when we talked about glucose, that from breaking down a single glucose molecule, we're going to get back 32 ATP. Well, with a molecule like stearin, where we have so many more hydrogens, rather than 12, we're going to get back many more ATP molecules, as you'll see here in a second. All right. So again, same basic chemical structure, but many more hydrogens, and obviously quite a few more carbons as well. So we'll talk about their structure here on the next slide, but in terms of the types of them, so we'll go over these in the next few slides, but the basic types of lipids, so you've got simple lipids, and by far the most common are your triglycerides, or on some slides it'll be referred to as triacylglycerols, because it depends on which book I was using when I was working on this, but know that those two mean the same thing, and I'm typically going to say triglycerides, even if it's an antiquated way of saying it. So your simple lipids include triglycerides. Compound lipids are a simple lipid plus something else. So for example, a triglyceride plus a protein, right? Or it could be a simple lipid plus a glucose, or plus sugar, or simple lipid plus phosphorus. So compound lipids then are simple lipids plus something else. And then derived lipids are effectively simple lipids plus a compound lipid. And so then you get a derived lipid. And the only one that we're going to talk about in the category of derived lipids is cholesterol. So with respect to simple lipids, again, by far the most common are your triglycerides. And so then you can see the alternative term there in parentheses, the triacylglycerols. So some of this stuff you're probably familiar with. So saturated, unsaturated fatty acids, you probably are at least a little bit familiar with the term. The picture there in the lower right, those are your adipocytes. Those are your little fat cells. That's what they look like. And then if we look at an individual triglyceride, this is the basic chemical structure of our triglyceride. So obviously tri is 3, sorry. And so what you've got here are these 3 fatty acid chains. So there's one, there's the second one, and there's the third one. And then those are attached to a glycerol backbone. And so they're triglycerides because you have 3 fatty acid chains attached to a triglycerol backbone. In terms of saturated versus unsaturated fatty acids, so thinking about the chemical formula I just showed you where you had a whole lot of hydrogens, so these little gray things are the hydrogens, little gray spheres, and then the green spheres here are the carbons. And so with your fatty acids, what they are these long strings of carbons with hydrogens bonded to them. So the typical length, they can range anywhere between 4 and 20, but the typical length is somewhere between 16 and 18 in terms of the length of the carbon chain. So in terms of saturated versus unsaturated fatty acids, the one that's in the picture here is a saturated fatty acid. And so what that means is that there are only single bonds. So these are covalent bonds, but there are only single bonds between the carbon, between each of the carbon, I want to say molecules, but it's probably not the most appropriate term here, but that's okay. So only single bonds between the carbons, as opposed to if we have an unsaturated fatty acid, then we're going to have a double bond between the carbons. And so why that matters then, in terms of saturated versus unsaturated, is that a saturated fat means that since there's only single bonds between the carbons, that every other bonding site available is attached to a hydrogen. So a saturated fat then is saturated with hydrogens, as opposed to an unsaturated fatty acid. So here's a saturated fat again. So, and what you get then from a molecular standpoint is that you get these long straight chains because of those single bonds. So here's a saturated fatty acid as opposed to an unsaturated fatty acid. So in the case of an unsaturated fatty acid, what you've got there, as you can see from this picture, is a double bond between 2 of the carbons. And so if you've got a double bond between 2 of the carbons, well, that's one less bonding site, if you will, for a hydrogen. And so because of that, that particular fatty acid is not fully saturated with hydrogen, so therefore it's an unsaturated fatty acid. So because of that double bonding, as you can tell, it changes the shape of the molecule, which then changes the function of the molecule. So between those two, if you have any sort of associations with them, oftentimes so saturated fats are typically referred to as being the unhealthy fats, and the reason for that is there's an association. If you have a diet that's higher in saturated fats, then you tend to have higher blood levels of LDL or bad cholesterol. And the reason that LDL cholesterol is referred to oftentimes as being bad, or has the connotation of being bad cholesterol, is that it has a high affinity for your artery walls. And so LDL cholesterol tends to lead to plaque deposits on the arterial walls. And so if you start to accumulate plaque inside of your arteries, well, a couple things happen there. One is that with that really hard plaque on the inside of the artery, well, it's going to lose some of its elasticity, right? It's not going to be able to stretch and then bounce back to its original shape. And then the other part of that is, as that plaque accumulates, obviously it's going to narrow the vessel. And so with that, if that vessel narrowing is in the heart, well, then that can lead to a heart attack if the vessel becomes fully occluded. Maybe a blood clot gets stuck in there or something like that, right? That can lead to strokes, pulmonary embolisms, any number of other things, right? And so saturated fatty acids often get this connotation of being unhealthy fats because, again, they're associated with increased levels of LDL cholesterol, which is associated with increased atherosclerosis. And so that's why then those become your unhealthy fats. where you find your saturated fatty acids. So those are found typically in animal products. So those are the fats that you find in things like beef and pork and bacon, which I know is a type of pork, and pigs are a magical animal. So that's where saturated fats are largely found, is in animal sources, but not exclusively. There are vegetable sources of saturated fats, so things like coconut oil and palm oil are saturated, are plant sources of saturated fats as well. So your unsaturated fats then, on the other hand, tend to come from your plant sources. Again, just because the plant source doesn't mean necessarily that's an unsaturated fat, but most plant sources are unsaturated fats. And so the two things on there where it says mono versus poly. So if you have a mono unsaturated fatty acid, that is one single double bond. And so the one that's pictured here is a mono unsaturated fatty acid because there's one double bond, as opposed to a poly unsaturated fatty acid. You're going to have more than one double bond, so you have two or more, right? So examples of mono unsaturated fatty acids are found in olive oil, peanuts, almonds, and avocados. Your polyunsaturated fatty acids tend to be found in places like sunflower oil, corn oil, and soybean oil. And so another thing, now that I'm looking at my notes, that I should mention is that your saturated fats tend to be solid at room temperature, or semi-solid, and then your unsaturated fats tend to be liquid at room temperature. So again, think about something like olive oil, right? So olive oil is a monounsaturated, or has monounsaturated fatty acids, and so olive oil obviously is liquid at room temperature, as opposed to if you have something like a steak sitting on your counter, the fat in that steak is going to be fairly solid, right? Because that's saturated fat. Where do trans fats come into this? So trans fats are made from unsaturated fatty acids. And so what ends up happening is that you can change those unsaturated fats into semi-solid fats by bubbling hydrogen into that oil under really high pressure. And so what that does when you bubble hydrogen into the oil under high pressure is to break those carbon double bonds, and it's going to attach hydrogen in their place, making the oil into a firmer fat. And so that's referred to then as hydrogenation. So anything that is partially hydrogenated, that's something that is a trans fat. And so if you're familiar with the term, if you've heard it before, again, probably has negative connotations, because again, those are manufactured fats. But the reason that trans fats are bad, and the reason that they are banned in some places, is that New York had a ban for a while. They still might, I don't know. But anyway, haven't really kept up with that level of food policy. But at one time, at least, New York had banned trans fats in their foods. New York City, not the state. And so the reason, their rationale for that was that trans fats are kind of a double bad, if you will, right? So I mentioned earlier that saturated fats increase your LDL or your bad cholesterol, and trans fats do that as well. But then trans fats also tend to decrease your HDL or your good cholesterol. So they're kind of double bad. They increase the bad cholesterol, leading to plaque formation, and they reduce the good cholesterol, which actually reduces HDL cholesterol. The reason it's quote unquote good cholesterol is because it tends to scavenge up those plaques and reduce plaque formation. So trans fats then are bad on both fronts. They increase LDL cholesterol, which speeds up plaque formation, and then they decrease the HDL cholesterol, which would decrease that plaque formation. So that's where trans fats come in. So if they're so bad, you might ask yourself, like, why would a company make those things? Why would that be something that's in food products? And the answer to that question is, the primary answer is that it extends the shelf life of those products. So you tend to find trans fats in things like your baked goods. So that may be things like cookies that sit on the shelf or can sit on a shelf for a really long period of time. Those tend to have trans fats in them. Sometimes crackers like Ritz, I don't know if they still do, but they used to have trans fats in them. And so not only does it extend the shelf life of those things, but it also changes the texture of them so they don't feel quite as greasy. So it's kind of a combination of those things where the food has a more palatable texture, again, not as greasy or oily, and it can stay on a shelf for longer. So that's why food companies would incorporate those into their recipes. So those are trans fats. And then in terms of the formation or breakdown of triglycerides, So we're going to make triglycerides in our adipocytes, in our fat cells, for example, after a meal. So if you have just eaten and you're not exercising, let's say you ate a meal and you're just kind of sitting around, so there's no real energy demands or not very high energy demands on the part of the body, what it's going to do then is it's going to make triglycerides. It's going to make more fat inside of your adipocytes, inside of your fat cells, so that you can store that energy. So in terms of the formation of triglycerides, it's stimulated very strongly by insulin. So obviously after a meal, typically you don't eat straight fat. There's usually some carbohydrates in there as well. And so after a meal, you're going to see insulin released to help bring down your blood glucose. But in addition to bringing down blood glucose, insulin, as mentioned, also drives the formation of triglycerides inside of your adipocytes. So in terms of mobilization or breakdown, so we're going to see the breakdown of triglycerides inside of the adipocytes or even inside of the muscle cells during exercise, or during physical activity is probably a better way of saying that. So during light to moderate physical activity, walking, jogging, those kinds of things, gardening, whatever it is that you're doing that is of relatively low intensity, that is going to stimulate the breakdown of fatty acids. We're breaking off fatty acids and kicking them back into the bloodstream so that muscle cells can use them. So in addition to exercise or physical activity, other things that stimulate the breakdown of so that's called lipolysis. Other things that stimulate lipolysis are low-calorie diet or fasting, right? So overnight, if you, like the example I used last time, if you haven't eaten in 12 hours or a long time, right, then that is going to stimulate the breakdown of fatty acids. Or cold stress is also pretty good at stimulating the breakdown of fat. So as mentioned last time, at rest and during light activity, fat is our primary fuel source. And so because it's easy to supply the oxygen needed to the tissues that are going to break down the fats, there's not a high oxygen demand, so it's easy for us to supply enough oxygen to meet the need to break down that fat. And so for especially at rest and low intensity, fat is the preferred fuel source of the body. All right. So those are our simple lipids. So now then on to compound lipids. So as mentioned, it's a triglyceride combined with something else. So the first one on there, your phospholipids. So your phospholipid is a triglyceride combined with a phosphate group. And so we talked about those initially way back in chapter 3. So remember that the membrane of a cell is a phospholipid bilayer, right? And so it's a fat combined with a phosphate group. And so if we have those in two layers, that then can make up our cell membrane. So those are your phospholipids. In addition to making up cell membranes, phospholipids are also involved in blood clotting. And then they also play a role in the myelination of nerve cells. Glycolipids, so remember we talked about glycogen last time, which is our storage form of carbohydrates inside of the muscles and inside of the liver. So anything glyco, there's going to be sugar involved. So glycolipids are a combination of a fatty acid with carbohydrates and nitrogen. And so where we see glycolipids is as part of the glycocalyx. Again, another throwback to chapter 3. Remember that the glycocalyx is the sugar covering of a cell, helps the cell identify itself, or helps the immune cells identify that that's one of our cells. So glycolipids then are involved in the formation of the glycocalyx. Lipoproteins. So obviously a lipoprotein, lipid is fat, protein is protein. So lipoprotein then are a combination of fat and protein. So lipoproteins are the major avenue for transporting fats in the blood. And the reason for that is if our blood lipids weren't bound to a protein, they would float to the top of the blood like cream, kind of, right? Instead of circulating readily. And so in order to circulate fats, to keep them from floating, and to allow them to basically kind of diffuse fairly evenly throughout the blood, what we have to do is attach those fats to proteins. And so the way those lipoproteins, the combination of fats and proteins, are classified is based on their size and their density and what they carry. So the first one on there are chylomicrons. We're going to talk about those in a second. But chylomicrons are formed when we absorb fats in the intestine. We're going to make those, and we're going to transport the fats as part of chylomicrons from the intestinal cell into the lymphatic system. And then from the lymphatic system, those chylomicrons are going to get dumped into the venous system. Then they circulate. And then they can be picked up by a skeletal muscle cell, for example. And then we can break them down. We can break the triglycerides down and then use it for energy. So chylomicrons are going to transport the fats that we absorb in the small intestine throughout the body. In addition to that, chylomicrons also play a role in transporting the fat-soluble vitamins, which are vitamins A, D, E, and K. So that's them till we get to the digestion here in a second. HDL cholesterol I mentioned a few moments ago. So remember that HDL cholesterol, or HDL, so HDL is a lipoprotein, and then we associate it with cholesterol because oftentimes it'll carry cholesterol. So HDL, so it's a high-density lipoprotein, and so what makes it high density? It's mostly protein, right? As opposed to the very low density, the next one down, or the low density, those have a higher proportion of them is fat, and so they tend to weigh less because fat tends to weigh less, right? So things that are protein tend to be heavier. So your HDL, the high density lipoprotein, has a higher protein content, so it's just a heavier molecule. But as mentioned a minute ago, HDL tends to get this reputation as being your good cholesterol. And the reason for that is because it can go through the arteries and essentially it'll scavenge up those atherosclerosis, those plaque deposits inside of the arteries, and it'll pull the cholesterol off of there, and then it'll take the cholesterol back to the liver, where we're going to then incorporate that into bile. So the HDL cholesterol helps us keep our arteries clear, helps us maintain our circulatory health. So that's why it gets the reputation of being good cholesterol. HDL cholesterol is increased whenever we engage in exercise, so particularly aerobic exercise. I haven't looked up the data on HDL cholesterol in strength training, but certainly with aerobic exercise, you get an increased production of HDL or good cholesterol, and so that's one of the ways that exercise plays a role in maintaining circulatory health. The next one on there, your very low density lipoproteins. So those are formed in the liver from fats, carbohydrates, or alcohol, and then cholesterol. And so the very low density lipoproteins transport triglycerides, transport those fats to muscle and fat cells, which are your adipocytes. The LDL, the low density lipoproteins. So again, remember that is oftentimes referred to as being bad cholesterol because it delivers cholesterol to the arterial tissue and then leads to that plaque formation. So that's LDL. So those are your compound lipids. Again, it is a lipid plus something else. So whether it's phosphate group, sugar, or protein, those are compound lipids. And so then we get to our derived lipids, which are a combination of the first two. So a combination of a simple lipid plus a compound lipid. So the most relevant for us in terms of the derived lipids, and in fact the only one we'll talk about, is cholesterol. So cholesterol generally gets a bad rap. So typically if you hear something about cholesterol, so Homer there eating his burger there in the lower right saying cholesterol, right? So the idea there is that cholesterol typically gets bad connotations. It's typically associated with lack of health, all right? But cholesterol obviously serves some pretty important functions in the body. So you can see there plays an important role in stabilizing the plasma membranes. So remember when we talked way back in chapter 3 about the phospholipid bilayer, I showed you the cholesterol molecules between the phospholipids that help them stay together, and it kind of reduces the mobility, it reduces the shifting around of those phospholipids, so it helps maintain the integrity of the plasma membrane. So cholesterol plays an important role there. Also serves as a precursor for vitamin D formation and as a precursor for the formation of sex hormones. So cholesterol, though it does tend to have negative connotations, does do some very important things. Another relevant thing to know about cholesterol is that somewhere between, depends on which textbook you look at, but somewhere between 70 and 85% of it is synthesized by the liver. So if you eat something that's high in cholesterol, that won't necessarily increase the amount of cholesterol in your blood, because in fact we make most of our cholesterol in our liver. Right? Now, of course, if you have a diet that's really high in saturated fat, the odds are pretty good that you're going to have more LDL cholesterol, more of that bad cholesterol. But again, we manufacture most of the cholesterol that is circulating. And so you can see, so the recommendation there, those are pretty general dietary guidelines. So the typical recommended fat intake is somewhere between 20 and 35% of total calories. And it depends, where I say it depends on composition. So typically the higher number is recommended if you're consuming a higher amount of your unsaturated fats, as opposed to the lower number is if the diet's higher in saturated fat, then you want to be closer to the lower number. So that's where that comes from. I won't ask any questions about that, but those are kind of general guidelines in terms of proportion of your calories that should come from fat. All right, so what do we use fats for? Well, obviously, one of the primary things that we use fats for is as an energy source. So, as mentioned last time, fats are a really dense supply of energy. And as talked about at the beginning of this video, there's lots and lots of hydrogens on our fatty acids. And so because of that, we can run lots of hydrogen through the electron transport chain and we can make lots of ATP. So they are very energy dense, which is a good thing about them. Also, they are dense relative to their weight. So they're fairly light. In part because they don't, so for example, your adipocytes, your fat cells, or your fatty tissue, there's not a lot of water content in that tissue, as opposed to your glycogen, so your intramuscular carbohydrate stores, that glucose pulls water with it, and so you tend to get, it's a relatively heavy fuel source. So all of the things that we can use anaerobically, ATP, phosphocreatine, and glucose or glycogen, those tend to be fairly heavy fuel sources. So fat doesn't have that disadvantage. It is relatively energy dense compared to its weight. So that's a good thing about it. One of the things I mentioned in the last video is that we can store about 2,000 calories worth of carbohydrates. So I think the number I gave you was 400 grams as muscle glycogen and about 100 grams in the liver. And I talked about how you can store 2,000 calories worth of carbohydrates, but we can store enough fat in order to get us all the way down the west coast of the U.S. So I have the more specific numbers here. So if we have an average 175-pound man whose body fat, whose body composition, I should say, is 15% fat, he has approximately 108,000 calories that he's storing as fat, right? So if you've got pretty average college student, again, 175 pounds, 15% body fat, male, then that person, that guy, has about 108,000 calories worth of fat. So that's enough energy in terms of assuming 100 calories per mile to get you from San Diego to Seattle on those fuel stores, as opposed to 20 miles on your carbohydrate stores. So a really efficient energy source. And again, the other side of that, of course, is that it becomes really difficult to get rid of it, right? Because it's such an efficient energy source. Other things that fat does, so protection of vital organs. There is visceral fat, as we talked about, that can play a role in protecting your vital organs. And you have fat pads throughout the musculoskeletal system as well. So for example, underneath your calcaneus, so under your heel, you've got a fat pad under there. You've got a fat pad underneath your patellar tendon. So you've also got fat kind of filling in spaces there. Thermal insulation, that's why the picture there on the lower right is there. I probably should have explained that earlier on this slide. So that's an English Channel swimmer, right? And so if you're an English Channel swimmer, it is advantageous to have a little bit higher body composition, so to be a little bit fattier than somebody who is something like a sprint swimmer, like Michael Phelps there at his prime, because that fat then enables you to, number one, float, because you're going to have to be in the water for hours and hours on end. But then number two, it helps you hang on to your, you don't lose as much of your heat to the environment. So it helps you maintain your core temperature, which would be an advantage if you're swimming in really cold water. However, if you're a sprint swimmer like Michael Phelps, well, you don't need that fat to float so much because your race is relatively short and you're going pretty hard the entire time. And so the buoyancy of the fat is not important. And so because of that, then you want to be as streamlined as possible. You want to have to move as little weight as possible. So, but nonetheless, fat acts as a thermal insulator, a vitamin carrier again. So the fat-soluble vitamins are A, D, E, and K. And if you don't have or don't consume enough fat, you won't be able to absorb those vitamins effectively. And then the last one on there is that it acts as a hunger depressor. So I mentioned previously that fat and protein take longer to digest than carbohydrates. And so because of that, meals that are higher in fat and protein tend to lead to more satiety. You feel full for longer. So because it just takes longer to break fat down in the small intestine, tend to feel full for longer. So that's a good thing about fat. All right. So in terms of the digestion of fat, so this is a pretty similar picture to what I showed you last time with carbohydrates. So remember, we need enzymes to break them down. In terms of fats, the enzymes that break them down are lipases. So we talked about that there's an enzyme that comes from the tongue, lingual lipase, that starts the breakdown of fat in the mouth. We get a little bit of breakdown in the stomach, but really where things happen is in the small intestine. So remember that once chyme moves from the stomach to the small intestine, that there's a common duct between the gallbladder and the pancreas. And so you're going to get this secretion of a combination of bile and pancreatic juice. And so remember that bile, what it does is to emulsify the fats. It takes those big droplets of fats and makes them into smaller droplets. And then once we've done that, then those lipases, so the ones that are part of your pancreatic juice, are going to have better access to those triglycerides and be able to break them down into their smaller constituent parts. So speaking of that, so what you've got here, so obviously starting at the top, we've got our big fat globule. So in this picture, we are in the small intestine. More specifically, we're in the duodenum. And so what I was just describing to you there was the secretion of our bile coming from our liver, right? That's where it's originally produced and then stored in the gallbladder. So the bile salts are then going to take this big fat globule and they're going to break it down into smaller fat globules. So that's the result of the bile. And then that's when our pancreatic juice or our pancreatic lipases come in. And so then they are going to break those fat droplets down. They're going to break those triglycerides down into monoglycerides and then free fatty acids. So remember, if we've got our triglyceride, you've got your glycerol backbone and then your 3 fatty acids coming off of it. The action of a lipase is to pull off fatty acids from that glycerol backbone. So you'll break off 2 of them, and then a monoglyceride is 1 fatty acid, the one, that still stays attached to that glycerol backbone. So starting at step 2 where it says pancreatic lipases hydrolyze, whatever, down into monoglycerides and free fatty acids, what that means then again is that we're going to pull off those fatty acids off of the glycerol backbone. So then the combination of those things, so the bile salts are still involved here, and so then we're going to form these micelles, and then we're going to absorb those component parts, right? So we're going to absorb those fatty acids and your monoglycerides and into the intestinal cells. So again, we're in the small intestine, we're in the duodenum, so here's your little intestinal cells. So we're going to absorb the fatty acids and the monoglycerides, and then we're actually going to reassemble them inside of the intestinal cells. And so we're going to form our chylomicrons, the things that I mentioned a minute ago. So those chylomicrons, as you can see, are a combination of those triglycerides, plus we're going to add protein to them. And so once we've packaged those triglycerides plus some proteins, then we're going to move that chylomicron across the basement membrane, so out of our little intestinal cell, and it's going to be absorbed into the lymphatic system. So whereas carbohydrates move into the circulatory system, initially your fats are actually absorbed into the lymphatic system. So remember, one of the things I talked about, I've kind of touched on the lymphatic system a couple times. The lymphatic system is involved in returning fluid back to central circulation. It's also involved in the immune system because you have white blood cells in there that will attack any invading pathogens, but it's, in this sense, involved in fat absorption. So we'll move those chylomicrons into the lymphatic system, which then dumps into the venous system, and then those chylomicrons are now in the circulation, and again, we can break them down into their component parts from there, and we can absorb, so we can break those triglycerides down, we can absorb them into our adipocytes, and then we can reform them as triglycerides inside of the adipocytes, and we can do the same kind of thing inside of muscle cells. Speaking of, so in terms of the sources of fat or where we store our fat, so broadly speaking, two places. So you can store fat in your adipocytes, which are your fat cells, and the vast majority of your fat cells are subcutaneous, so underneath the skin. You do have, as mentioned a little while ago, you do have visceral fat, right? So you got adipocytes around your organs as well, but the vast majority of the fat that we store is actually just underneath the skin, so that's our subcutaneous fat. And then we have our intramuscular fat. So intramuscular fat, as the name implies, is inside of muscle cells. So that is predominantly, almost exclusively, inside of your slow twitch fibers. It's in some of the type 2A, the kind of intermediate fibers as well. But we can store triglycerides, or you can store fat inside of your muscle cells to provide a fuel source, just like glycogen, inside of the muscle cell. So whereas we carry about 2,000 calories, including liver glycogen, in terms of glycogen storage, and with respect to intramuscular fats, we store about 3,000 calories worth of that, right? So a pretty good amount of again, using the 100 calories per mile, about 30 miles worth of intramuscular triglycerides. So just so quite a bit of energy stored inside of the muscle cells alone, not even accounting for the amount of energy that we store as subcutaneous fat and elsewhere. So I mentioned earlier the concept of lipolysis, the concept of breaking down our fats. So what happens there? Well, when you engage in low to moderate intensity exercise, or you're cold, or you're dieting, the things that we talked about, let's stick with physical activity, right? So if I engage in exercise, so I decide to go out for a jog or a run. So when I do that, I'm going to release two hormones, epinephrine, norepinephrine. There are others, but among the hormones that I'm going to release includes epinephrine and norepinephrine. And so both of those two then stimulate lipolysis. They stimulate fat breakdown. And so HSL is hormone-sensitive lipase. And so this is our subcutaneous fat here. And so in response to our little adipocyte or adipose tissue receiving epinephrine, norepinephrine, that's going to cause hormone-sensitive lipase to become more active, and so it is going to break down our triglycerides into our free fatty acids, and then we'll pull off that glycerol backbone, and those go through different paths. Once a free fatty acid goes into the blood, we have to, again, bind it with a protein so that we can transport it in the blood. And the particular protein that's going to transport most of those fatty acids is called albumin, and you can see the spelling of albumin down here. So we're going to bind those fatty acids with albumin so that we can transport them in the blood, and then they can be picked up by a working muscle cell, for example. We can move it into the muscle cell, and then we can break it down there. The glycerol, so the backbone to our triglyceride, is actually so it's also going to go to the muscle cell in that example. And where the glycerol comes in is that it's actually going to come into glycolysis just after step 5. So the glycerol backbone then enters just after step 5. When we fully metabolize that glycerol backbone, that itself is going to yield 19 ATP. So we get a decent amount of energy coming from the backbone of the fatty acids before we even get to the fatty acids themselves. So why I mention the hormone-sensitive lipase and the production or the release of epinephrine, norepinephrine, is that when we start exercising, you're going to release those two hormones, and you're just going to generally mobilize fat throughout the body, right? Because one of the things that people oftentimes believe with respect to exercise is the idea that you can spot reduce. So if I feel like I have lots of fat in my abdomen, and so I need to work on that, people sometimes concentrate and do lots and lots of ab work, right? So lots and lots of crunches under the assumption that if I'm working the muscles underneath that subcutaneous fat, well, then those muscles are going to actually use the fat that's sitting on top of them. So that's spot reduction. Or you see the same thing. So I'm not proud of it, but I have a membership to Planet Fitness in addition to Lifetime because I'm that kind of a person that has multiple gym memberships. But one of the things I see working out at Planet, or at the Planet, is they have machines where it is resisted hip AB and AD duction. So when I was working at Gold's when I was in college, oftentimes women, so I was a personal trainer, women would come in and say, well, I really need to work on my triceps, the back of my arm, because it kind of flaps around a little bit, and I need to work on my saddlebags. Those are terms that I heard pretty consistently. And so when I talk to them about that, oftentimes I say, what are you doing for that? And they'd say, well, I'm doing the machines where you sit there and you pull your legs apart, and then the other machine where you pull your legs together. Because if I'm doing hip AB and AD duction, I'm going to use the fat that's on top of my hip abductors, and so because of that, then it's going to give me a slimmer hip, right? And so they were conveying an idea of spot reduction, but that's not how it works. So when you exercise, again, you're just going to release epinephrine, norepinephrine, and they're going to stimulate lipolysis throughout the body. So the actual fat that I'm using to fuel that exercise may not come from my abdominal fat, may not come from my lateral hip fat, but in fact it may come from atop my biceps or atop my triceps, something like that. So you can't spot reduce, I guess is the short version here, because of the way that the endocrine system works and the way that we engage in lipolysis, the way we break fat down, where it just happens throughout the body. Just because you're using a muscle underneath that fat doesn't mean that that muscle is going to use the fat that is closest to it in terms of subcutaneous fat. So short version is, can't spot reduce. It's not the way it works. All right, so once we get that fat into our muscle cell, for example, so remember that your fatty acids are those long strings of carbon. So again, oftentimes between 16 and 20 carbons long. What we're going to do then is we're going to break those fatty acids into little 2 carbon fragments. And so the process to do that is called beta oxidation. So again, in this process, what we're going to do is chew that up. So if we have a chain of 18 carbons, we're going to break that down into 9 2-carbon fragments. And then once we've done that, those little 2 carbon fragments come into the citric acid cycle. Just before it starts, they come in as acetyl-CoA. And then just like pyruvate, so here's the end product of glycolysis, which then we make into acetyl-CoA. Fat's going to come in at that step, and then the acetyl-CoA goes through the citric acid cycle. We then pull off all the hydrogens that we talked about, and then as you can see here, we bring those hydrogens over to the electron transport chain, pull off their electrons, establish that gradient, all the stuff that we talked about earlier, and then attach those hydrogens to water, blah, 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 right? So we break them down using the citric acid cycle and the electron transport chain, and so then the result is, again, because you have so many hydrogens in your fatty acids, we got lots of things to put through the electron transport chain, and so we end up making lots and lots of ATPs. So as mentioned earlier, the glycerol backbone itself, you get back 19 ATPs from breaking that down and going back a slide. So here's our little glycerol coming in, again, just after step 5 in glycolysis, and then it runs through the rest of the process. And then we use beta oxidation, that's what this is. So again, beta oxidation is breaking that long string of carbons into 2 carbon fragments, comes in as acetyl-CoA, goes through the citric acid cycle, goes through the electron transport chain, and then we end up with 441. So this is breaking down stearin, that fatty acid that I showed you at the beginning. And so our typical 18 carbon fatty acid is going to generate 460 ATPs. So lots and lots of energy, lots and lots of ATP generated from those fatty acid molecules, right? So as mentioned, a really efficient fuel source. So you saw this picture last time. So remember, the gist of it is, so we've got so plasma glucose down here is the orange, so your blood sugar, and then we have our plasma free fatty acids, so fat in the blood. So that's the fat that you mobilize that I was mentioning earlier from hormone sensitive lipase. Also glucagon. So remember that insulin and glucagon are antagonists. So if your blood sugar gets too low, you'll release glucagon also from the pancreas, which is going to stimulate the breakdown of fat. And so that's going to elevate our plasma-free fatty acids, and then we also have our intramuscular triglycerides here. So this is a slow walk. This is kind of a jog or a slow run, and then this is a pretty hard run over here. So how much fat we use depends upon, as you can see, the intensity of the exercise. So as the intensity goes up, we become increasingly reliant on carbohydrates to fuel that exercise, again, because the transfer of energy from carbohydrates is so much faster, right? Because to break down carbohydrates, number one, we can break them down anaerobically, or get back ATP anaerobically from carbohydrates. But number two, there's just less steps in the process. As opposed to fatty acids, you got to mobilize them, get them into the fat cells if you're not using intramuscular triglycerides, and then it has to go through beta oxidation, then it has to go through the citric acid cycle, then it has to go to the electron transport chain, and we have to have oxygen available. So fats then takes longer, and there has to be oxygen available in order for us to break them down. So the more intense the exercise, the more reliant we become on carbohydrates. So for low and moderate intensity exercise, we're going to use fat as the preferred fuel source. Now that said, our ability to use fat depends upon our conditioning status. And actually, before I move on to that point, the last thing on there says use of fat depends upon carbohydrate availability. If there's carbohydrates available, that blunts or reduces fat usage. So if you, before you exercise, eat some gummy bears or drink a Gatorade or anything else that's going to supply carbohydrates, well then you have an readily available fuel source, and so then the body's going to use the carbohydrates instead of the fat. So if there's carbohydrates available, then that's what you're going to use. But if there are not, and you're doing low intensity, low to moderate, then you're going to use fat preferentially. All right, so now we're on to the second bullet point. So the relationship between exercise training and fat use. So you can see there that increased body fat is associated with decreased ability to use fat during exercise, which seems weird, seems counterintuitive, because you'd assume the more fat you have, the better you'd be at using it. But it's not the case, because unless you have lots of endurance training adaptations, in which case you probably don't have increased body fat. But with exercise training, with endurance training more specifically, so remember that we're going to get adaptations in the muscle cells that include more capillaries around those muscle cells, more mitochondria inside of those muscle cells, and more of the citric acid cycle enzymes. So in response to endurance training, if you've got more mitochondria, you have more places to break down fat, and you have more of the enzymes in the citric acid cycle to help you do that. And if you have more capillaries, you have more surface area to diffuse oxygen into the muscle cell to get it into the mitochondria so that we can get rid of those hydrogens, right? So the adaptations associated with exercise training, or with endurance training specifically, enable us to use fat more efficiently. So this picture, or these two pie charts, come from, I think this one's from a 12-week endurance training study. And so if you look at individuals coming into the study, so these are sedentary individuals coming into the study. So when they do an exercise test, endurance exercise test at the beginning of the study, their primary fuel source is carbohydrates. And they only use about 25 or 24% of the energy comes from intramuscular triglycerides. That's what the IMTG stands for. And then 18% from plasma fatty acids. And then after 12 weeks of endurance training, so you're going to get more capillaries, more mitochondria, more citric acid cycle enzymes. And so because we're able to break down the different macronutrients aerobically more easily, because we have more of the mitochondria to do that, more of the capillaries to supply oxygen, not to mention the cardiovascular adaptations that we've talked about previously. So you're able to deliver oxygen better to the muscle cells, and the muscle cells are able to use it more effectively. Because of that, we can use fat more effectively. So after the endurance training, so after again 3 months of endurance training, the intramuscular triglyceride usage goes up, it almost doubles, so to 46%. Plasma fatty acids actually go down a little bit, but the overall fat use goes up pretty significantly, so carbohydrate use dropped from 58% to 38%. And so the result of that is, with training then, we can use fat at progressively higher intensities, because you've got, again, you're able to supply the muscle cells with oxygen, got more places to use it, and so with that training, again, you can use fat at higher intensities. If I'm using fat at higher intensities, I'm not using glycogen, so that's glycogen sparing. And so I can hang on to my glycogen for longer. So maybe I won't deplete my glycogen until I am 22 miles into the race instead of 20 miles into the race. And so that enables me to perform at a higher level for longer. So that's a really important set of adaptations. All right, so last but certainly not least is our proteins. So, like carbohydrates and fat, so proteins also have carbon, hydrogen, and oxygen, but in addition to those, they also have nitrogen, right? So they also have the amine group, which contains our nitrogen. So in terms of the protein makeup then, or the amino acid makeup more specifically, so you've got the amine group that contains your nitrogen. You have the organic acid side group, which is over here. And then you have the R group, or the side chain. So that is going to vary between different amino acids. And again, in terms of terminology, the amino acids are your building blocks for your protein. So you're going to string together a bunch of amino acids, and if you string together enough of them, then you have a protein. And so proteins vary in length. They can be tens of thousands to, I think the biggest one is dystrophin. It's a couple 100,000. So they can be really, really long strings of, or really long, really big molecules that include lots and lots of amino acids, right? So the R group, or the side chain there, those vary between the different amino acids, and so that's what gives each one its particular structural and functional characteristics. All right, so the short thing to know there, that your proteins, the way they're different from carbohydrates and fat, is because they contain nitrogen. All right, so in terms of types of amino acids, so you've got essential and non-essential. From a dietary standpoint, anything that is essential is something that the body can't make. So what that means then is that you have to consume it. So you even have essential fatty acids as well. We didn't talk about those. Those are your omega-3s and your omega-6s. So you don't need to know that. But anything essential then, like I said, is something that you can't make, so you have to consume it. So your essential amino acids, there are 8 of those, and so in the picture in the lower right, you can see all of the essential amino acids plus the 2 that are essential in babies. So these 2, and so those are a list of essentials, and then we have our non-essential amino acids. So what non-essential then means is that the body is able to synthesize those from other compounds, and there are 9 of those. So 8 essentials, 9 non-essentials, and then a couple terms there: complete proteins versus incomplete proteins. So complete proteins are those that contain all of the essential amino acids. So conversely, as you would expect, your incomplete proteins are ones that lack one or more of those essential amino acids. So oftentimes, your animal proteins are the ones that tend to be complete proteins. So good sources of complete proteins include eggs, fish, beef, cow's milk, and poultry, and pork as well. It's included under poultry, right? I think so. Anyway, meat, basically. Meat, eggs, milk, dairy products, under which milk, of course, falls. It's getting late. So the animal products then tend to be your complete proteins. They tend to have all of the essential amino acids, as opposed to your plant proteins, other than soy, and there's maybe one other one that I'm missing, but your plant proteins, by and large, are your incomplete proteins. And so if you're a vegetarian, that's okay in terms of you can still get complete proteins if there is enough overlap between the different proteins in the various plant sources that you eat. So one of the things, if you're a vegetarian, is you have to make sure that you're getting a variety of different plant sources of protein, and that way hopefully there's enough overlap between the different plant sources that you get all of the essential amino acids. And so what you've got pictured here in the lower right is that corn and other grains contain all of these essential amino acids, but they're missing isoleucine and lysine, right? But then your beans and your other legumes have valine on down to lysine, but they are missing tryptophan and methionine. And so the idea here is that if you eat a wide variety of incomplete proteins, hopefully the overlap between the two generates a complete protein. And so oftentimes, as part of various cultural diets, you'll see that their plant sources that are oftentimes staples of the diet comprise or include complete proteins, or account for, I guess is a better way of saying that, complete proteins. So for example, beans and rice, so like red beans and rice, or oftentimes in if you are into Mexican food, as I am, there's usually some kind of rice and beans on the side almost all the time. And so the idea there is that, or what that does is between those two, between the rice and the beans, you end up with all of the essential amino acids, so you end up then with a complete protein. Another thing that I should mention here is the concept of the all or none rule as it pertains to proteins. And the all or none rule is that all of the amino acids needed to make a particular protein must be present in a cell at the same time and in sufficient amounts in order to produce that protein. If one of those amino acids is missing, then the protein can't be made. So, that's the all or none rule. So if you don't have a particular amino acid, you can't make the protein at that time, right? And so that can then become problematic. All right. So in terms of energy released from protein, part of the reason I saved it for last, and I don't talk about it as much, is that we don't really get a whole lot of energy from protein. We don't really use it to produce ATP. We can, but in general, we use carbohydrates and fat, right? And so protein, for example, if you have somebody who is well-nourished, at rest, about 2 to 5% of their energy production needs come from protein. So it is a very minor player in the energy production process. So one of the other things about proteins is, and where they differ from carbohydrates and fat, is that we don't have a protein storage area per se, right? So in the case of carbohydrates, you can store them as glycogen. In the case of fats, you can store them in the adipocytes, but there's not really a place where we can just store essential amino acids and use them for later, right? So the skeletal muscle cells are kind of that. They act as a protein reservoir, but really only if we are, if we fasted for a long time. Then we'll break down our muscles and we'll actually, for example, convert those amino acids to glucose in order to use them for energy. But by and large, we don't have a storage area for protein in the same way that we do for carbohydrates and fat. So if we're not going to incorporate those amino acids into muscle cells, for example, or if we're not going to help them or use them to help us make collagen, then we're going to pull off the nitrogen group. That's deamination. So that happens in the liver. And so we're going to pull off the nitrogen group in the liver, and then we're going to get rid of it. So that, as you can see there, becomes urea, which is excreted through urine. And then whatever's left, that remaining carbon skeleton, a variety of different things can happen to it. One is that we can convert it to a different amino acid, and again, that's going to happen by and large in the liver. So that's called transamination. You can make it into a different amino acid, so a different protein that you need. So that's where the non-essentials come in. So I mentioned that they're non-essential because we can make them from other things, and so we can do that in the liver, for example. You can also do it to a limited extent in the muscle cells, but most of that happens in the liver. We can also convert the remaining carbon skeleton into carbohydrates. So you can make them into, we'll leave it at that. You can make them into carbohydrates. And then you can also use them for energy. So and I'll show you where that comes in right here. So the different amino acid skeletons come in at different points in the citric acid cycle, but the vast majority of them come in somewhere in the process of the citric acid cycle. So you can use them for energy, but again, it's something that we oftentimes, or we typically don't do. Or I say that. So you're doing it all the time, you're just not doing very much of it as compared to carbohydrates and fat. In terms of nitrogen balance, so if your nitrogen balance is positive, that is anabolism, means you're building tissue. So you see that in kids and infants and pregnant women. So if you're building a bunch of new tissue, that's where you see that. You also see it after resistance training. So if you go lift weights for the next maybe 72 hours, you've increased your protein synthesis. So you're building new tissue. You're building more muscle, more actin, more myosin, etc. And so that is anabolic, making more tissue than you're tearing down. Negative nitrogen balance is catabolism. So you're tearing tissue down. In terms of the importance of carbohydrates, so carbohydrates acts as a sparer of protein. So for example, if you are exercising first thing in the morning, fasted, and you haven't eaten in hours, as we've talked about several times, one of the things that you'll do, particularly if your liver glycogen has become depleted, again, the central nervous system, neurons need glucose to run on. And so what you'll do to get that glucose is you'll break down muscle. And again, while we don't have storage of protein per se, the muscles kind of act as that protein reservoir, and so you'll break down muscle, and you'll then convert those carbon skeletons into carbohydrates. And so where the importance of carbohydrates comes in is, if you're a high-level athlete, you don't want to be breaking down muscle tissue because you work pretty hard to build it up. And so the idea is that if you have a sufficient amount of carbohydrate, then that'll help you maintain muscle mass. It'll help you keep from breaking down muscle mass and using it as fuel. In terms of protein dynamics during exercise, again, protein's contribution to energy production is really pretty minimal. So, and you saw that on that last that table I showed you a couple times about the balance between carbohydrates and fat depending upon exercise intensity. All right, so the key points for this whole thing, the key points for Chapter 4. So for exercise beyond 90 seconds, so beyond like an all-out, 2-lap sprint, or really 1-lap sprint for many of us, that we have to rephosphorylate, remake ATP aerobically, which means with oxygen. And we can accomplish that by putting macronutrient constituents through the citric acid cycle, breaking off hydrogen, and taking them to the electron transport chain where they're combined with oxygen to create water and regenerate ATP. But an important aspect of that, or important thing about that, is it takes a long time and it's a lot of steps. So where the aerobic side of things kicks in is there's a little bit of a lag time there because you have to increase heart rates, you got to increase oxygen delivery, you got to dilate the blood vessels where it's needed, and all of that stuff. So there's some lag time in the aerobic metabolism. Plus, because it takes a while and it's dependent upon oxygen delivery, we can't maintain the same amount of power as we can breaking down energy or producing ATP anaerobically. Another thing to know is that all of the energy production pathways improve with specific training. So anaerobic training increases stores of ATP, phosphocreatine, and glycogen. So anaerobic training in this sense meaning like lifting weights, sprint training if you're a sprint type athlete like volleyball players. Over the course of the season, some of the adaptations the muscles will be that you can store more glycogen, and then you also have more of the enzymes to break that glycogen down. So the glycolytic enzymes, those 10 enzymes that I showed you in glycolysis, you'll actually make more of those. So you get better at breaking down glucose to produce ATP anaerobically. On the other side of things, if you train aerobically, so if you do endurance type training, then you get better at breaking down the macronutrients aerobically. So you get those adaptations that we talked about, or I talked about a minute ago, more capillaries around the muscle cells, more mitochondria, more citric acid cycle enzymes. So again, you get better at producing energy aerobically. So why does that matter? So if you're an athlete or a future coach, there is some specificity to those adaptations. So a perfect example comes up when I was at a previous institution, another Division III institution. One of our volleyball players said, well, we're getting ready to, because it was the off season, so it was probably December-ish, that they were getting ready to start training for one of the local half marathons. And so she said, yeah, coach really wants us to train for this half marathon, so a 13.1 mile run, to get us in shape for the spring volleyball season. And so do you think that's a good idea? And so the answer to that question, of course, is no, because you're never going to have to run 13.1 miles over the course of a volleyball game. A volleyball athlete is very much a sprint athlete, right? So they have to be very explosive, very, very quick movements and relatively small distances that they're covering, right? And so they use the ATP phosphocreatine system plus the glycolytic system. And so they want to maximize the efficiency of those systems in their training. And if they then go and do a bunch of endurance training, well, what they're going to do is actually quite the opposite. So they're going to get more capillaries, more mitochondria, all those aerobic things that are good for endurance training, but those aren't really going to bestow any benefits when they get back on the volleyball court. Plus, there are a whole host of other issues related to motor unit recruitment and movement efficiency that they're also going to dampen by engaging in endurance training. But as it pertains to this discussion, if you're a pure sprint athlete, you want to maximize those anaerobic pathways. And if you're an endurance athlete, you want to maximize those aerobic pathways. So the adaptations are specific to your training. And that's it. So that's all of chapter 24. So you made it through all of it. So good luck on test 3. Good luck on the final. And certainly email me if you need anything. Thanks for watching.